Okay. So, next class is that let us go for the filtering view of STFT. So, what I said that if I in DFT view that n represent the number of band we have analysis. Okay. So, can I not think that I have a signal, I want to analyze the signal for a particular band. So, if I say this is a band pass filter, so I analyze the signal for this band, then analyze the signal for this band. So, I can say this is nothing but a, if I have a signal, pass the signal over a different band pass filter, and each bandwidth is nothing but a 2 pi by n. So, this is at a nutshell the filtering view of the STFT. So, in mathematically how it will be represent? So, I can say I want to find out the output frequency response for a particular band or a particular signal, particular frequency omega 0. So, I have a signal xm, I want to find out whether this xm contains omega 0 or not. Whether this xm contains omega 0 or not. Forget about the windowing part I am coming later on. So, what I will do, you know that to get that output, what I done a convolution in time domain, I do a convolution for a particular, I generate a particular frequency signal e to the power j omega 0 and convolved with xm, that is my DFT equation. Okay. Now, if it is window, then I have not taken the whole signal at a time. So, I cut the signal using a window. So, I can say x of n omega 0 for a particular frequency, it is nothing but a m equal to minus infinity to infinity x of m e to the power minus j omega 0 m. This signal multiply by the window. This is my window. Okay or not? So, I can say I find out the convolution of the particular component with the signal, and then the convolution output pass through a multiply with the window, or I can say if this is my things, if I remove this bracket, then I can say it is nothing but a convolution of x of m e to the power minus j omega 0 m convolved with my window function. Is okay or not? So, if it is nth time instant, so I fix the time instant, then I can say it is the nth portion of the signal, is find out the frequency component omega 0 with the nth portion of the signal and convolved with the window function. It is same when the time instant is fixed. Now, if it is that, what is the meaning of that? What is the convolution? If I have a system Hn is a system response, system impulse response, if I have a signal at xn, if I pass the xn with Hn, what is the output? Yn is nothing but a convolution of Hn with x of n input signal. So, if my x output frequency response is nothing but a convolution of this term with window function. So, what is this term? This is nothing called a frequency shifting or modulation. It is nothing but a modulation. If I multiply, let us cos omega t, multiply by another cos signal, cos omega 0 t. What is that? Let us carrier signal and multiply with the baseband signal. So, output is cos omega c plus omega 0. If I cos omega 0 and cos omega c minus omega 0. Okay. if it is to j, instead of cos, if I multiply with the shifting, so that means omega c will be shifted to omega 0. Omega c will be shifted to omega 0. So, if I say that only, then I can say this convolution, if I want to draw the block diagram of this convolution function. So, instead of m, I should write n, I should not write minus m, because time instant I have taken n is the fixed time instant. So, instead of minus m, I write n. Okay. So, if I want to draw the signal diagram of or system diagram of this thing, so I can say this is my x n is coming, it has to be modulated by e to the power minus j omega 0 n at particular frequency. This is the modulation. Modulation means multiplication. Then it has to be passed through a system whose filter impulse response is W n, and I get the output which is x of fixed time for a particular frequency response. Okay. So, if I draw the whole frequency response, suppose the baseband signal, okay, I delete this one, baseband signal x m has a frequency response of this. This is the frequency response of x m. So, x m to, or I can say x n. So, this is x n and has a frequency response of x omega. So, this is x capital X omega. Okay. It has to be modulated by j omega 0 n. So, once I modulated, then I can say this is my j omega 0, this frequency band. Instead of omega 0 single frequency, let us omega 0 is a band. So, this is my omega 0. Okay. If this is my omega 0, then what will happen? It has to be once I do the modulation. So, this origin has to be shifted. So, this will come here, I get this is nothing but a omega plus omega 0. Modulation is done, shifted to omega 0, origin has to be shifted to omega 0. Once this is called modulation, once this modulation done, I have a filter whose impulse response is W n, but frequency response is like this. This is the frequency response of the filter. So, it is nothing but a capital W omega. Okay. Once this is passed through this time domain convolution, frequency domain multiplication. So, this will be multiply here. So, this portion is my output I get as a x of n omega 0, which is nothing but a x of omega plus omega 0 multiply by W omega. Okay or not? Okay. Now, I can shift this notation. Instead of writing this way, I can write this way also. What is the way? X n omega 0 is nothing but a e to the power minus j omega 0 n x of n convolve with the. So, what I am doing, instead of convolving the frequency response of the signal, let us convolve the frequency response of the window. So, instead of doing this, what I will do, I write this is my frequency response of window W omega, or sorry, okay, this is W omega. Let us modulate this thing to here. Okay. So, I modulate this thing to omega 0. So, instead of omega in 0 frequency, I can say let us at omega 0 it is come in omega 0. Okay. I shifted that things to omega 0 and I pass this thing to a filter which only filter out this portion. Okay. Or what I will do, okay, explaining it. So, what I want to do is that instead of writing W, I can say I can get the W omega. Okay. So, once I get the W omega, that is the frequency response of the window, pass the baseband signal with the frequency response of the window. So, if the baseband signal is frequency response is this one, then this window will become here. Okay. So, I pass the this signal is passes to this. So, this portion will be there and rest portion will be not there. So, this portion will be not there, only this portion will be there, which is omega 0. Now, if it is omega 0, I have to shift this to here. So, what I will do, I will multiply this with the e to the power j minus j omega 0 n. So, what will come? This will come to the here. So, at output filter, this will be shifted or demodulated to come to origin. So, this can be one view. Then the diagram will change. What should the diagram? That first pass the signal, this is my x n, pass the signal with a window frequency response W e to the power j omega 0 n. Then demodulated, shift the frequency with e to the power minus j omega 0 n. That also possible. Then also I get x n omega 0. Now, if I generalize this equation, instead of omega 0, I can write, instead of omega 0, I can write k. Once I write k, then this omega 0 is become 2 pi by n k. This omega 0 is become 2 pi by n k into n. Okay. So, I can write analysis equation in filtering view that the same, that I have a signal x n, x n is my signal. I have framed the signal first. X n is a fixed length signal. I am thinking this signal consists of several frequency component and I design a several band pass filter with a fixed frequency band and each band pass filter is shifted to a particular frequency. So, what I am doing, if this is my frequency scale, I design a band pass filter 1, this one, second one will be here, third one will be here, fourth one will be here. How do I do that? Each bandwidth is 2 pi by n. So, this is nothing but a shifted frequency. So, I can say, I write down the synthesis equation, synthesis diagram, this is my x n. Okay. So, this is my x n. So, this is 0th component when k equal to 0. So, 2 pi by n into k. So, k equal to 0. I can write what is this omega 0 w n into e to the power j 2 pi by n into k equal to 0 into n. Then demodulate it with e to the power minus j 2 pi by n k equal to 0 into n. Then I can write again w n e to the power j 2 pi by n into 1 n, again demodulate it, e to the power minus j 2 pi by n, k equal to 1 n. So, dot 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 I can write w n e to the power j 2 pi by n into k n multiply by e to the power minus j 2 pi by n into k n. So, each of the output, this is nothing but a x, if it is n, nth instant with 0 frequency. This is output of x, nth instant with first k equal to 1, then x n 2, then it is nothing but a x of n k. So, this is called synthesis part. So, analysis with discrete STF. So, I can say this portion is called analysis of STFT with filtering view. So, I can say I apply the xn signal, I can find out the 0th component, first component, second component, third component and kth component this way. So, this is x 0 1, this is, forget about this portion, do not see this portion, let us try to hide this portion. I just hide this portion, let us design insert shape, you hide this portion. This portion I will discuss later. So, now this portion is the analysis portion. Now, in synthesis portion, what is my requirement? From there, I have to apply some process by which I can sum up them and apply the inverse transform. I should get back the xn, that is the synthesis portion. So, if I remove it, if you see, if I remove it, that same those inputs are going there and some kind of the inverse transform is taken care and that inverse transform is written here. I will discuss the details in inverse transform and then I get the xn back. If omega 0, w 0 is not 0, then we exactly recover the signal, that we will discuss, which is called synthesis. So, STFT analysis, this is the STFT analysis part, synthesis part I will discuss in the next class. Okay. So, there is some property, if you find any book, there is some property of the STFT analysis. I am not reading the slides, you can read the slides better. Now, come to the another things which is called time frequency trade-off. Do not think about the mathematics, there is a mathematical part is there in the slides. I am not, I just describe what is time frequency trade-off. If you see in any DFT or STFT analysis or STFT, there is a two words, one is called time. I have taken a small segment of the speech signal and I have applied a frequency transform, number of band, that is k. So, let us I take a signal of 10 millisecond which contain 160 sample. So, n length of the DFT is the nearest 2 to the power something, unless I have to put more 0 padding and the amplitude will vanish. So, what I will do, nearest 2 to the power something. So, if it is nearest, then I can say it is 256, let us 2 to the power 256 n equal to 256. Okay. So, I take the n equal to 256. Now, what is the resolution? If the signal is 16 kilohertz sample, n equal to 256, then I can 16 k divided by 256 is my resolution. Now, if I want to increase the frequency resolution, so instead of 10 millisecond, if I take 20 millisecond, then it is 320 sample, then I can say n is equal to 512. If it is 512, this is the resolution. So, now resolution comes 512. So, resolution is increases. What is the resolution? Resolution means this is a frequency scale. If I divide this long window, so that resolution is less. If I want to increase the resolution, the division has to be very small size. So, 2 pi by n value, if it is decreased, then resolution is increased. So, if this will be decreased, 2 pi by n will be decreased if n is increased. So, once I increase the n length of the DFT, then I require a large number of signal at a time. So, if I take a large number of signal, this is the time axis. So, instead of short segment, if I take a long segment, then what I am losing? I am losing the time resolution. So, if I increase the frequency resolution, I decrease the time resolution. So, that is called time frequency trade-off. If I take a larger amount of signal at a time, my frequency resolution will be very high, but I lose the within that time the variation of the signal I lose. So, the time resolution will be decreases. So, if I increase the frequency resolution, time resolution decreases. If I increase the time resolution, frequency resolution will be decreases. Okay. So, that is the time frequency trade-off in STFT analysis. Then there is another topic is called effect of window. Different window has a different effect. What I said, whatever the frequency response I get, which is x n k, this is my output of frequency analysis n omega, this is nothing but a convolution. So, what I am doing, a signal is multiplied by a window. So, time domain multiplication, frequency domain convolution, that means this is nothing but a convolution of frequency response of the window and the signal frequency response. So, what is meaning? Suppose if I have a window of rectangular window, you know the frequency response of the, what is the frequency transform of the rectangular window? Is nothing but a sinc function, nothing but a sinc function. So, there is a peak main lobe and there is a side lobe. So, that will be, and the main lobe width depends on the length of the window. Okay. So, that will be convolved with the frequency response of the original signal. Okay. So, the effect of the window will be always there. Once I multiply by the window, so the frequency response is not the exact frequency response of the signal. So, it is the frequency response of the main lobe multiplied by the side lobe. So, what I want to increase the main lobe should be flat. Ideally, if the main lobe is flat, then the side lobe, effect of side lobe, it is negligible. Then I can say the frequency response whatever I get, it is exactly the frequency response of the window. Okay. So, if you see there is a different kinds of window is there. If you remember that I have given in the review of DSP that Butterworth, the Blackman window, Hamming window, Henning window, Kaiser window. So, and different window has a different kinds of frequency response. Okay. So, my intention is that main lobe width has to be increased and side lobe attenuation must be very high. Side lobe should be very slow disturbing. Then I can say the analysis of frequency analysis of the signal is almost preserved. So, that is my effect. So, I want to choose such a window whose main lobe width is very high. If you see in the spectrogram, when I discussing about the spectrogram analysis in this software, there is a, if I just open a sample English file, English voice file, and if you see that setting, spectral analysis setting, if you see there is a window, Hamming window, triangular window. So, depending on the window function, the frequency response will be different, because the effect of window frequency response will be transferred to there. So, if it is Hamming window, something else. If it is Henning window, if it is Hamming, Henning, then it is different. So, depend on the window, the frequency response is different. Even if I do the spectral analysis, analyze spectral by scan, see that there is a different window selection, Hamming window, Hanning window, then Blackman window, then Kaiser window or Gaussian, and this is the FFT size. So, this is the choice of n. If I this choice, if the frequency resolution is very low, if I go there, frequency resolution is very high. Okay. So, depending on the choice is there window size and window and windows. So, window size will come from the length of the your FFT. If n is equal to, if the window length is 20 millisecond, that means 320 sample is there, then my n is fixed to almost close to 320 is 256 no 512. Okay, because it is implemented in FFT. Okay. So, length of the window has tied with the frequency or time resolution, and type of the window I will choose what kind of details analysis I want. Maximum cases in speech and Hanning window is used. Okay. So, next class I will discuss about the STFT synthesis. Okay. Thank you.